Welcome to Snap Education Step 3 of the execution phase. To keep in mind the Snap process and where we are, let's do a brief summary. Snap is a three-step process. We have seen in Step 1 how to adapt the application and the function so that the function could be used in a FPGA with additional resources. We have seen in Step 2 how to adapt the software action to a hardware action and have simulated the whole code. And we are now going to see deeper the Step 3. In this Step 3, we are now going to build the image of the full design which will be running in the FPGA and see how to execute it on a real FPGA plugged into a power aid. After having simulated the code in Step 2, we have no more code to modify. We are going to compile the same code tested and executed on the simulator. The command to be typed from the Snap directory is just a make image. This process takes an hour, and during this hour, Snap is going to take all the code, meaning all your hardware action, but also the different drivers to the resource you need, a DMA to discuss with the PSL, the job manager, the different drivers to the different memories, and all logic used to handle your action transparently. The Vivado tool will place it in predefined FPGA logic resource, connect all resources together, and ensure that the logic is synchronously working together. Once all this is done, process will create the binary file containing the image of your design and which will be put in the FPGA. Now that your image is built, meaning that Vivado has generated the bitstream binary file, let's copy this bin file to the PowerAid server so that we can write it into the FPGA card and then execute it. On Nimbix, the instruction to type is the instruction deploy to power. For your information, this is a script that you can find in your home directory. This command in Nimbix will download the binary file into the FPGA memory, then reset the card, but also create the instance so that we can execute the program. If the instance creation is successful, then you'll get in your dashboard the instance snap ppc64le deploy of the PowerAid instance associated to your physical FPGA card. If no FPGA card is available, your request will be queued until a card becomes free. So, now we are in the dashboard and let's wait to have the Docker instance created to be able to access it. This takes a couple of minutes. The Docker is now created. Let's open it and we can see that it comes with the README text file, which will help you to go through the flow on the PowerAid. These instructions are specific to the PowerAid. Once the terminal of this instance opened, you'll find the README file where all instructions are provided. Clone the Snap GitHub as you already did it on the x86 instance, and use the Cloud Branch release, which guarantee you that you'll use a tested release. Set path using source snap path sh and the action root variable to the action you are testing, and finally compile the application using make software apps. Now, let's localize the slot available for your card. If you have chosen the Alpha Data KU3, then type snap find card -A ADKU3 or copy paste it from the README file. you will get the slot in which the ADKU3 has been found. In this case, you can find it in slot 0. Let's now run the discovery program command snap main -v -C0 for slot 0, which displays the setting of your card. As in Nimbix, the card you can access will always be in slot C0. You can even omit to specify the -C0 argument. The result of this command shows that the action available in your FPGA is the HLS Hello World action. Now that the card has been discovered and the action identified by the job manager, we can execute the HLS Hello World application. Let's create a file with a mix of upper and lowercase characters and call it T1 for example, or copy the line from the README file. Then call the application, snap Hello World, the result shows the success status of the action and the execution time reported by this action. You will certainly argue that such time is quite long for such a simple case. So it's important to explain here that the time reported includes the time to set all of the registers of the action, plus the time to fetch the data into the server memory, to go through the algorithm, copy back the result in server memory, and at last read the register's values. Even more, this code doesn't contain on purpose any optimization at all, since this will be studied in an aside module. Let's now look to the different files and check that the work was done okay. All the characters have been converted to uppercase, which is what is expected. You can also try the snap trace option, as well as the snap config equals CPU to test all other options. A typical error that you may see is the fail to attach action. This is typically when the user has forgotten to run the snap main program before calling his application. Just execute snap main and then the snap Hello World application. If the error relates to the card attachment, check that you have set the correct slot number to the -C argument. And at last, if nothing is reported, depending on the system you are running on, you may have just missed the sudo instruction before your comment. Third and last step is now completed. We have executed the application on the Power8 CPU and the hardware action on the FPGA. We just used a single make image to compile the whole design for the FPGA. Process is now completed. A module 4 can help you measuring now performance of your code and how to optimize it. Congratulations, you did it! You just offloaded a function initially running on your server processor to an external FPGA card which has even more new resources. Just imagine now how simple it is to get a text from an external storage and process it or filter it to just bring the results directly in server memory without any processor interaction.